Okay, thank you very much. And since I'm the last speaker of this week, so I would like to thank Riddhi and all other organizers of this for excellent conditions, everything. Thank you very much. Okay, my goal kind of to look random walks in random growing domains. It could be discrete time, and our continuous time could be Brownian motion. Then there are technicalities. So general situation is described like that. Suppose we have sequence of domains. So that's what's written in first paragraph. So you can think discretely, D1, D2, and each one contains previous one, etc. And then you have domain D1, and you have random walk walking in this domain. So this walk is in prison, so you cannot go out of this domain. So you can define in various possible ways how this random walk is reflected. For example, if you are in discrete situation, when you come to the boundary, then you choose uniformly among vertices which are lying within domain. You could take reflection. Suppose you come to boundary point, and then boundary pushes you back to the vertex from which you came. So there are a variety of things, and they actually, at the end, will really little matter to me. But then you are well-behaved prisoner in this prison, so prison is large, so you get better conditions. And then now you forget that you were imprisoned in cell D1, now you are in cell D2, which is bigger. And you continue. Okay? And again, you are constrained. But still you behave well, and then you are given even bigger domain. And all this goes to, say, we are on the graph ZD. Interesting case, D bigger or equal than 2, and in particular, when we speak about transience and recurrence, D is bigger or equal than 3 on ZD. So what is going to happen to this random walk? Okay, that's a question which I would like to address. So, of course, intuitively clear, if this D1, D2, D3 are blowing up very fastly, then actually random walk essentially will not even feel that he is in prison. Okay? So this thing's running away. So we can have continuous situation that dt, they evolving continuously, but what is important at this step, what I'm describing, that evolution of these, no matter if it's discrete or continuous, it's independent of walk. So they're just growing in their own way. And random walk is living in this randomly changing environment. It could be some function, and then, as you see, I have some assumptions. So what you can say about situations? So the first assumption says that these dt are well behaved. So I'm looking at particular case of growth of dt. So function f, it's rate of growth. You know, how fast or slow you are developing. So this already suggests that if function f is very slow, sublinear, etc., heavily sublinear, it sort of keeps random walk trapped in any dimension for a very long time, then increases slowly away. So what strength of this f should be that even in the higher dimensions where free random walk would be transient, it succeeds to trap you. Okay? And then, of course, it's generally a very open question, and I will, in some minutes, tell you motivation why suddenly we start to work on that. But then there is special assumption that this f should be such that it keeps this set D kind of nicely behaved. So you have two balls, radius 1, say, and radius c. C could be arbitrary, but fixed number. And then this dt is sort of contained in growing balls B1 times ft, BC times ft, and your shape is somewhere here. dt is lying somewhere here. Okay? And then, based on some heuristic kind of calculation, etc., with Samir Dembo, Rujun Huang, and myself, we conjectured a couple of years ago that actually work is transient if and only if this function gf is integrable. Okay. Somehow looking, there is no big mystery in this computation, because if you think that your d is kind of nice shape, dt is itself some ball which lying somewhere here. It doesn't need to be growing with the same rate ft, but it always lies in between. Then if you do kind of rough computation of return probabilities, it's reflected from this ball, then it kind of indicates that this situation should occur. And indeed, we could prove something towards this conjecture here. So here is main theorem, and main theorem actually says that work is recurrent if and only if this is integrable, except that we cannot prove for even within kind of this class of assumptions. So we need to take something more. So, and first something more, that not every function we can deal with. And I will explain why. And second is that not every domain K in which you are moving is allowed. And then let me explain why. So these conditions are really technical conditions which we involve in the proof, because if you look at this process in discrete times, so you can take constantly evolving function, kind of constant, then it jumps, and then these are conditions on how this function is jumping, the rate function. So piecewise constant. And so it says that this function cannot really evolve in an arbitrary way. So these are sort of distance between heights, how long you stay constant. So you stay, then increase prism, etc. Could do the same continuously. But technical condition is this one, that this A's, we cannot take arbitrary function. Again, this comes from computation, so we just cannot deal if it is not. So this is just first attempt. And this condition that shape of these, which are lying between two balls, have to be special. I don't want to enter in details of definition of this case special, but it has to be rather smooth, because you can take, for example, shapes which satisfy this condition. They are lying in between for all times. However, these shapes could be pretty nasty, like that. And you can imagine this sort of fractality of the boundary of the shape, and then random walk can enter here and stay for a very long time in this fjord, and then fjord has other sub-fjords, etc. So you can still satisfy conditions of assumption, but this fractality sort of sucks you close to the boundary. And that's a problem. So this we don't know, even though it's nice, but it can be trapped for a long time in this type of fjords. Okay, so that's actually our arch enemy, fractality of the boundary. So now this example, it's actually very interesting and has even in this simplistic situation, open problem. Suppose now since we are in FPP weekend, suppose you have now these evolving in time as first passage percolation. So here is the model. You have first passage percolation, take arbitrary passage time which are decent, so for example exponential passage time. And then random walk performs continuous time random walk also with exponential rate of jump. So now we know that you have shape theorem, so Guy evolves very nicely. We can say something about fluctuation. So this set, FPP set, moving linearly. So you say, but random walk who stays here is diffusive. So somehow you lose this cluster's boundary and you will never see it again because he goes linearly. And here is difficulty. So lots of people try to answer this question that this random walk is actually transient in dimension 3, for example. And if it's not clear that this random walk is recurrent in dimension 2, which looks strange, but actually it is not, again, the same arc enemy, this situation. So on the boundary of cluster, which evolves independently, again you have fjords. Okay? And you enter this fjord, you stay a long time, boundary evolves of this FPP, it will take everything eventually, but by the time this guy comes, it produces new fjord. And suddenly you start to be trapped in fjord, so as if you're surfing on boundary of cluster, entering in constantly appearing fjords. So nobody believes this happens up to infinity, but no even idea how to tackle these things. And the same situation with of appearance of arc enemy. It's IDLA cluster. IDLA cluster. So these sets are evolving as IDLA cluster. Suppose you launch particles from the origin in continuous time. Okay. And then, of course, this now cluster itself grows much slower in time. I'm talking about radius. So particle is bouncing. And again, the same effect is that you can enter in fjords of boundary of IDLA cluster, even though boundary fluctuates logarithmically, right? But nobody prevents us to enter very long sort of hairs inside and get stuck in these hairs for a long time. And then again, it evolves, and then something. Of course, we don't expect to have such hairs. But again, no proof or understanding. But what I want to say, these situations, when you see, they are situations when random walk doesn't affect growth of reasons, of clusters, which sort of surround these sets. Okay? And my interest is to get to the situation where, even though we cannot treat these cases, to the situations where you have set these evolving dependently on random walk. And first example would be modified IDLA again. So everybody knows IDLA, should I remind? So IDLA is the process where we have discrete evolution of sets, and so at time 0 you release particle, say ZD, and this particle grows until it reaches set which first point which doesn't belong to AT. You add this point to AT, and now this set is your AT plus 1. Then again, you go back to the origin, you release particle, when it comes first time outside of set AT plus 1, you add this point, and it's your, now this one, it's your AT plus 2, and so on. So we know everything, but essentially what you would like to know at the first sort of stage, that there is limiting shape and fluctuations. But now let us change the game. And changing game means that now center from which you launch particles is moving itself. Okay? So lots of efforts were done and still stay obscure. So there is, to my knowledge, only one work by Dominique Copin, Beniamini, Gadi Cosma, and I'm very sorry, there is some else plus. So what they analyze IDLA, but which is modified. Let us call MDLA. And what is modification? That when particle is launched from some point and then hits somewhere boundary, and you include this particle, new launch point is chosen uniformly on the previous area. So you did this, you choose uniformly some point, and then again the same story. You add, you don't go to the origin, but you just choose uniformly. It's quite technical work to show that actually this process also has limiting shape. They don't have fluctuations, I guess, but at least they know that it converges to Euclidean ball. It's this launching. So it was at some time among people interested in these questions, third modification, prime of IDLA. And this model actually is related to what I'm going to talk on later. So now again, you create a shape by launching particle from position X. It goes, adds something, okay? This is your new shape, but this launching point now performs random walks. Makes a step, launches a particle. Makes a step, launches a particle. Okay? So this starting point is moving around, is reflected on the boundary if it hits it. For example, launcher could come here, and it launches particle, and this particle could travel an add point here. So launcher cannot go outside. Okay? But it's likely, if launcher came and it's random walk, that you start to launch particles, and some percentage of these particles will come to closer point. So you're producing sort of bump. Okay? So this process is highly irreversible, and question is again, so what you have here? So this is open. This launcher. Okay. All right. So that's more or less set up, sort of where I'm going to work. So this we know. So this answers very, very much partially case when growth is independent of random walk. And essentially we don't have other nice examples which kind of give you some extension of this. But still what I'm saying, this we believe is kind of universality conjecture for this class of Fs. Should be unsensitive to fractality of the boundary. All right. So now examples I gave. Okay, so my main topic, actually that's why I started to look at these things, is once reinforced random walk. So once reinforced random walk comes from 1990. It was introduced by Burgess Davis in desperation because nobody could solve the Connes linearly reinforced random walk, and this is supposed to be kind of lighter. So it turned sort of around. So linearly reinforced random walk is understood by several means, by different teams. And once reinforced random walk is not. So now let me just give you some brief idea. And I am now, after phase transition for once reinforced random walk, depending how strong reinforcement is and in which dimension you are. Okay, so you have graph. This I am doing to explain figures which are coming. So you start from the origin, and you are giving weights to your edges, initial weights at time 0, say 1. You can give actually random weights as written here, like omega, and it doesn't need to be 1. And then game starts. So you go from the origin, first step, you choose uniformly any edge, which is around because weights are equal. But once you cross edge, weight of this edge becomes 1 plus delta. Of course, you can take delta positive and negative. If it becomes negative but smaller than 1, then it somehow loses weight. And if delta is positive, which I'm always assume, delta is positive, then this edge gains weight. Okay? You are here, 1, 1, 1, and this is 1 plus delta. If delta is very small, you essentially don't feel difference. So if delta small, really small, you can do very easy coupling, saying that you, for 1/delta steps, will not feel influence. So you move somewhere without really caring that it was delta. This becomes 1 plus delta, 1 plus delta. Okay? But delta is small, and then feeling is that as for a long time you move as random walk, and then eventually clock rings, 1/delta, and then you feel it. Okay? But so you are producing some set. And when you are inside of this set, again, everything now becomes 1 plus delta, 1 plus delta, 1 plus delta, so you move as simple random walk. You don't feel weights. And you start to feel weights only on boundary points. So again, if delta is very small, so when you come here, so this is 1 plus delta, but you essentially more or less don't feel up to some point. And this grows as if random walk trajectory with some sort of defects. But now if delta is huge, then this change becomes substantial. So you make your first step from here to here. And this edge becomes extremely heavy. And, well, supposed to be red. You are here, so you are not willing to go here because this edge calls you back. And then again, you go back, but it's once reinforced random walk. It's not linear, so weight doesn't change. But again, here is some 1, 1, 1, 1, and here is zillions. So again, you stay moving here for a while, but of course, with probability 1, you will go out. So you get another red. But again, for some reason, the same reason, you are moving somehow on this red set. And this set, with probability 1, of course, will go out of its current shape. You cannot be trapped in this set, because within this set, suppose now this area all is red, then again, inside of this area, you are moving like simple random walk. But eventually you come here, and after many attempts, so you come here, you try to go, but you don't go. You move somewhere here, you try to go, but you don't go. But eventually, with probability 1, you will get new area, and game continues. So you are building shape, but which somehow doesn't allow you to go out. But you will go out with positive probability. So Now, again, coming back to prison growing sets, except that this set which traps me is constructed by random walk itself. It's not growing independently of random walk. And then, naturally to think that if delta is very small, you look like random walkish. And if you now in dimension ZD, D bigger or equal than 3, if you are random walkish in this dimension with small deltas, then you suppose, or it feels you should be transient. And if you trapped by such prism, and here comes the question, should you be recurrent in any dimension? And then some years ago, some years, it would be like 15 years ago, I conjectured that if delta, so okay, let me write precisely. For any d bigger or equal than 3 exists reinforcement delta, which depends on dimension delta, such that if reinforcement, or let us call critical delta, which depends on dimension, if reinforcement is smaller than delta, critical, recurrence, transience. Because this delta cannot really trap you. And if delta is bigger than delta critical of dimension d, recurrent. For, essentially, this should be true for any decent graph. Doesn't need to be ZD. In fact, trees, and soon we will boil to the tree. So it was unclear if this conjecture is true. And for dimension 2, which is not really my particular interest for today, there are results by Burgess Davis himself, then results of Silke-Rolles and Franz Merkel on ladders in dimension 2, that it is recurrent for any reinforcement. Or maybe not, so sorry, in ladder, there is some value that it's recurrent, so it's not clear what happens outside of this region. But there is a quite known article by Duret, Kesten, and Lada-Limich, which says that on any diary tree, random walk, once reinforced random walk is transient for any delta. So no matter how you want to push it back, it doesn't work. And proof rather involved in their case, and that was like, I don't want to lie, but around 96. And then Andrea Colavecchio gave very elegant proof, not only covering the result of Duret and Kesten, but essentially saying that on every tree which has exponential growth, it's transient for any reinforcement. So here, in this situation, there is no phase transition. So is this conjecture true, that exists phase transition or not? And I have been working a lot on that. And, okay, let me see. So what leads to this conjecture? So until recently, we had only simulations. So this simulation is done by Arvind Singh from Paris, and this is two-dimensional case. But for you to see how shapes are built. So this color difference is just evolution in time, And reinforcement here, if you take initial weight 1, I think it's 2. And you see it's sort of fractalish set. And so this is small scale simulation, and he had done very large simulation. And actually this shape sort of doesn't change morally. It's very kind of fractalish. But now I will increase reinforcement. You see, it's just moving from 2 to 4 reinforcement, and it immediately becomes sort of bulky, but with terrible boundary, which kills any attempt to say something. You increase a little bit more just by 1, it's 5. You see shape is getting sort of roundish, and if I can say smoothish, if you can call it. Go further, and then increasing by 1, it gets, at least looking at the picture, even more roundish and with lessier fluctuation. And then he did really large-scale fluctuation simulation, and you get a picture like that. So clearly, this boundary is not logarithmic in this picture. Okay? Some kind of rougher. And now, to connect with FPP. So if you remember IDLA, which is well behaved, evolution of IDLA, classical IDLA, where you start from the origin, is governed by harmonic measure from inside. So if you produce some sort of things, you kind of will erase. And actually, the process is driven by harmonic measure. But what happens here? And here, sort of heuristic argument. Give me any number you prefer R, positive, and think of them as big. Then I claim that I can find exists reinforcement delta such that, and will depend on R, but I don't want to do it now explicitly, such that the following will happen. You remember processes that my random walking, bouncing on the boundary either let it go or sends back and you are moving in this area. And then suppose I consider situation, just to make simpler for you to understand, I take initial conditions, some small disk, radius small r. Okay? And start from the origin. But delta now should be thought as very large. And large in the following sense. I go, move, I try to bounce outside, but delta is so large that in this attempt I don't succeed. I move, bounce, I don't succeed. I move. So if delta is very large, my first success, roughly speaking, will be after 1 over delta bouncing. Okay? I will do some step. And then again, I continue bouncing and bouncing. Then again, 1 over delta steps, I have no success. I add some bump. Where I'm trying to arrive, that in this situation, you do next bounce, you can prove, actually we can prove that you get essentially mixed. And then your next bump is going to be placed uniformly on your set. So your set becomes something after some time. And again, you are staying in this cage and bouncing, and it's uniformly. What is that? That's essentially Eden. Because now I am not about time, I am about shape. So I don't really worry for the moment how long it takes to you and you add something. So, but what I'm saying, on small scales, you did this bump, but resistance of outer area is so large that essentially you are getting well mixed before you put new bump. Okay? So at first level, it develop like hidden model, and there's place where I'm fitting to the workshop. But what happens later? So you're already in huge area, which is essentially FPP, and then R is something which lies inside. So I can sort of get this delta, but delta is fixed forever. And so what starts to happen afterwards? I start to do locally FPP, but then I lose, and I go somewhere, then I start to do locally FPP, but now, you are not sort of mixing well here. So if you come here, you are staying here. You are not sort of going somewhere that I can claim you are mixing. But what I can do, essentially, think the following way. It's actually looks like you come here, you work here, make a bump, then go something deeper, then again go somewhere. But this picture is already highly not FPP picture. So FPP type or Eden type evolution are kind of in local bumps, but then this next scale evolution, I already cannot keep it, cannot claim that it's actually FPP. So it looks like you will be eventually coming to the origin, and then again do sort of, and this picture kind of increases with scale. So if I say a little bit like that, that it's kind of governed globally by IDLA principle, but locally you produce bumps. That would be intuitive understanding of things. So, but again, there is no proof, and I will go back to this question. So, so it was not clear, especially looking at Duret, Kesten, and Limich result, that this conjecture is true at all. So there is somehow negative answer to this conjecture by them on regular tree. So how can we do? And then it took some years to this. And this is three-dimensional picture, so it's the same principle. So it looks like three-dimensional walk, but it's kind of fatted, and then again gets sort of bulky, and eventually really goes to a ball. So there's not so much. All right. So in 2017, with Daniel Kiyus, finally we found example of a graph, TD, on which this conjecture is true. So probably everybody knows this graph from book Doyle and Snell, where they prove recurrence of random walk in 2 dimensions. So this graph has polynomial growth. And I'm not sure you can see. So how this tree is constructed, you take sequence of numbers, this is 0, 2, 4 powers of 2, and you will be allowed to branch only at points which are powers of 2. So your branching gets slower and slower and slower, and in between branches, you look like, if you enter this branch, like you are having one-dimensional walk. And then you choose. So this is T3, and and TD, you branch in the points. So here is the theorem. So we were very happy to have this. So random walk with parameter delta is transient if delta is smaller than log d divided by log 2 minus 1, and recurrent if it's bigger. I will not speak about proof. We were very happy, but it was, if I could say, handmade. We were very lucky to get this number. And why? Because it brings us to next step of story, branching ruin number. So maybe some of you know, some don't. So in '67, Furstenberg studied kind of some fragmentation processes, and then he introduced notion. So he used actually kind of three structures, and then in his work he introduced something really very deep and important, which is kind of, he called Hausdorff, or three-dimension, which is kind of Hausdorff dimension, if I can say, on average. I don't want to go into details. And then this notion was used with huge power by Ross Lyons to study processes on trees. And actually, he was the first who introduced the branching without ruin number, and essentially Furstenberg's Hausdorff dimension is just log of branching number of Lyons. Okay? And it essentially measures what happens on average around each point. Okay? This notion particularly powerful when you study polynomially growing trees, because for exponentially growing trees, so I will go to definition, this notion is kind of not as useful. Okay, so what is branching ruin number? It tells you a lot about graph structure from local view to global view. So, and the definition of branching ruin number is here, and let me explain now. So you look at a tree, and then you want to say how many ways you can go away. So cut set. It's a set of edges. And now I am going to this definition, because why is branching ruin number and Lyons has branching number? Because definition actually as formula is the same, but different. What is different? Definition of cut sets. So there is some slight modification. So cut set is a set of edges. So you have a tree. And then cut set is set of edges which prevent self-avoiding walk, because we're talking about walks. So self-avoiding walk, so escape from the origin. So cut set could be this one. This is a cut set, and this could be cut set. So you look at all possible cut sets on the tree, which. So and then pi is the set of all cut sets. So it's associated with the tree. So having this, you know already a lot. And then branching ruin number, it's supremum over all lambdas. Such make this, if you look at this sum, and take infimum over all pi's, over all elements of cut set. So that's the definition of branching number. So in particular, for example, if you have regular tree, this branching number is infinity and it doesn't tell you much. And then we could prove very general theorem. So it's it was kind of beginning of 2018. So if you fix any locally finite 3G, and then there is branching number of the tree, which could be between 0 and infinity, including both. And then very precise criteria is that once reinforced random walk with parameter delta is transient, if it's smaller than branching number, so it means that this Hausdorff dimension, which branching number represents actually is not capable, is so relatively weak that if delta is small, it cannot really trace you back. And recurrent, if delta is bigger than branching number, then this reinforcement beats this kind of Hausdorff dimension back. That's very general theorem. It works for very arbitrary trees, which, I mean, for most of trees. Only there are few pathological exceptions, but so this existence of phase transition now is completely understood on trees. And Kesten's case is here also, just because in Kesten's case, recurrency, if delta is bigger than branching ruin number for regular tree, this number is infinity. So it actually incorporates and Kesten's direct Kesten and Limich result. So that's more or less what we know today about this transition between recurrence and transience. So what happens on ZD? Of course, it's entirely open. D is bigger or equal than 3. And where's problem? So problem is that we do not know very well how to do the normalization procedure. So somehow renormalization scheme by itself is rather transparent and I would say even simplistic. So if you believe in those pictures which I showed, this ball, or better to look at this, then what you want to do, let's pretend that we already in sort of nice situation, except that we don't know what is boundary fluctuation, but now your walk comes. And we know that if this is huge radius, you are not going to only produce little bump here, but you are going to stay around. Random walk goes back, then has positive probability to go back here, and then you are working in some, let me call L1 scale, which is saying that you are kind of drilling in a ball of radius L1. But eventually, you will come deeper inside, but probability still to go to origin before you touch here is not so large. Then you come back and again produce something of scale L1. And then again you go backwards, maybe somewhere here, etc. But after a certain number of attempts, depending how reinforcement is strong, let me put, you go deeper even, and then you start to work here. So now, how do you renormalize? You would like to say, when you come here, you get some kind of clean box, and then you get clean box, and then you get clean box, and then you come back in this region, and again you do something else, and then maybe you produce something of scale L2. And then again, go back, and then maybe go back. So here already scale 1, and then you produce scale L2. After a certain number of scales L2, you come back and then start to build things, and you produce scale L3, and so on and so on. So what you want to prove? You want to prove that this somehow is behaving sort of regularly, which means that when you come here, you come to the box, and you start to invade this, invade this, invade this. So I know that if this scale L1, you will stay time of order L1 square, just moving around. And during this time of L1 square, you will knock L1 times on the boundary. So you clean sort of first layer. But this is not true. You may clean after number L1 bounds, some kind of producing fjords. And that started kind of, many people were pessimistic at that point, saying that all this picture, it's relatively nice because even it's huge scale, but it's still small scale for global behavior. That eventually, you will start to behave like three-dimensional walk. You start to produce like that, but then eventually you start to dig some sort of channel. And this renormalization, okay, I am finishing in 1 minute, and this renormalization, I firmly believe it should work, but it relies on very, very delicate control of local times of random walk, which leads to another set of problems, because you don't want to, I mean, belief is that by the time you reach here, actually everything of order L1 square will be destroyed. So that's more or less situation for today. And so there is some article by Rujun Huang, Daniel Kius, Pierre Therese, and myself, trying to catch these local times. And in very, very simplistic situation, but associated with this first step of renormalization. And it's kind of, in fact, remarkably, it has some connection with Gaussian free field, which I would never expect myself working on that. But okay, thank you very much. And